So your book has guidelines for solving applied minimum and maximum problems. These are also, by the way, called optimization problems. Identify all given quantities and all quantities to be determined. If possible, make a sketch. That oftentimes helps just to organize your thoughts. Write a primary equation for the quantity that's being maximized or minimized, just like I did in the previous problem. Reduce the primary equation to one having a single independent variable. So that's using the constraint to help us write that. We might have to use, here it says use secondary. It's also sometimes called a constraint. Determine the feasible domain of the primary, that's if it has endpoints or not. That is, determine the value for which the stated problems make sense. Determine the desired maximum and minimum value by using calculus techniques. I kind of have in my own way of wording it. Step number 1, understand the problem, which means read it carefully and ask yourself, what is the quantity to be maximized or minimized? That's really the starting point. What is the quantity which it depends on? Write down what to optimize. So that's really where we're starting. Now, a lot of times I will start with a sketch, but just to get a picture of what's being talked about. But really, that's where I want to figure out, like, that's what I'm basing everything on. Step 2, draw a diagram. Sometimes more than one diagram helps. You determine how all the quantities relate. Identify all quantities in step 1 on your diagram. Step 3, assign variables to the quantities from step 1. So basically you're using, like, if you're using x and y and h. In the previous problem, we had x and h and v. Determine a function for the quantities to be optimized. That's writing the equation. We will use here, eliminate all but one variable and determine the domain of the resulting function. This usually requires a secondary equation, also called a constraint. Step 6, optimize the function. Calculate the derivative and find the critical numbers. If the domain is a closed interval, compare the function's value of the critical numbers with that of the endpoints. If the domain is an open interval, use the first or second derivative test to analyze the behavior of the function. So you end up with 2 options there. So let's try a problem. Example 2. It says, which points on the graph of y is equal to 8 minus x squared are closest to the point 0, 4. Okay, so in this particular case, we want to optimize by finding the minimum distance. And I used the letter L for length. And the way we do that is using the distance formula, right? So we're finding all of the points on a particular parabola. If I was to sketch this here, right, up here, I want to find at any given point on this parabola, xy, is where do I get the shortest distance between that point and the point 0, 4, like that. So that's why I'm using the distance formula. Oh, and here, maybe I should change it to D then for distance there. Whoops. All right, so then we have the constraint. Didn't mean to erase all of that. Constraint, y is equal to 8 minus x squared. Now in this case, you don't really need to draw a diagram. I drew it up here just to help me explain, but it's not necessarily a requirement, but it's helpful. In our, here, whoops, rewrite D in terms of x. So I'm then here, look, for this particular y, I'm substituting in the constraint, y is equal to 8 minus x squared. And then polishing it off a little bit and simplifying in here. Like that. So based on the distance formula, right, we had x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. The square root of that is the distance formula. And I'm using these 2 points here, the general point and then the point I'm finding the distance to. and then simplifying a bit. And then once I know what y is in terms of x, which is given, the constraint is actually just given to you. So then I'm just substituting that in for y and simplifying. And then we could do a little bit more math, expand out, for example. So I'm expanding that 4 minus x squared squared. That's all of this right here. And then combining some like terms and simplifying a little bit more from there. So let's look what we get in the end here, like that. Okay. Let's think about it for a minute, by the way. We're taking the derivative, and we're trying to minimize or make it the smallest possible. A square root is always going to be the smallest if its radicand, that's the stuff inside, is smallest. So we could kind of cheat the system a little bit and only concentrate on minimizing inside the radicand. You could also do the whole thing. I'm just trying to simplify it a little bit. So if you just took the derivative of the distance and then went from there, terrific. But if you think about it, my object is to minimize. The only way I'm going to get a minimum value is if the radicand is the smallest. So we can kind of get away with just taking the derivative of the radicand. But again, I'm going to treat that interior of the radicand, f of x, and I'm going to minimize that instead. If you didn't think of that and you just went ahead and did it traditional, like the whole thing with the radical, great. It also works just fine. I'm just trying to simplify if you could think of it, right? So we're taking f of x and just concentrating on the radicand and then taking the derivative thereof. And then going from there, I'm just going to take, I can use the power rule and then simplify. If you used the entire radical, you would get the same in the numerator. You would just happen to have a denominator. That's all. And okay, we need to then set that equal to 0. So we take f prime of x is equal to 0 when 2x times a quantity 2x squared minus 7 is equal to 0. So that happens in 3 places. I just solved for each one of those x for each of those factors. Now, you could leave it as 0 and then the square root of 7 halves and negative, but you tend to not do that. I rationalized as well. This just kind of depends. It looks a little neater that way, not to have a fraction inside a radical. And then, okay, based on that, since the domain for x has no endpoints, in this case, because x, it's a parabola, so it will go on, it's for all real numbers, then we must use the first derivatives test to make sure that we get a minimum value. So we need to test all of those values here at negative, the critical numbers are at negative square roots of 14 over 2, 0 square roots of 14 over 2, and see where we get positive and negative. So I'm just substituting in values in those intervals. I picked, by the way, a value that was like really low so that I know I'm definitely to the left of negative 14 over 2. And then some value in between there. I know that the square root of 14 is the closest to square root of 16. So that would be 4 over 2. So it's definitely like closer to 2 than it is to 1, so, negative 1. So it's reasonable to use a negative 1 for the next interval to test. And remember, we're literally only interested in the sign here. So we're just looking at what each sign is going to be. So if I look at this piece here is going to be negative for both of those. And then we just have to concentrate on it in here. Do we get a positive? So here we have negative times at times in there. Negative 10 squared is 100 times 2 is 200 minus 7 is definitely positive. So that's how I know that this is going to be a negative there. And then for this negative 1 now, it's different. It's going to be a negative times, and then this is going to give me a negative. So that's how I know it's going to be a positive. And then similar reasoning over here. So for the 1 and the positive 10. So this is what we get. We get a negative, positive, negative, positive. Now, when it changes from negative to positive, you know you have a relative minimum. When you have, when it changes from positive to negative, it's a relative maximum. But I'm interested in the minimums only because I'm looking for the closest. But you could write in here that you have a relative max, but it's not like useful in this problem. These are the two I want to concentrate on, here and here. So that means then we have relative minimums there let's just double check here. The minimum happens at positive and negative root 14 over 2. Both of them happens to give you the same value. So you can substitute in both a positive and a negative, and you will get the same thing. You will end up getting square root of 14 over 2. So that means the closest point on y is equal to 8 minus x squared, 2, 0, 4, must be either this one or this one. It's going to be the same on both sides. So it's here or here.